Unit 4, Lesson 3, Solve equations by BEDMAS backwards, matching bases, or trial and error methods. So there's different ways an equation can be set up as, and we need to solve for the x, and these are the three ways that we're going to do that. We're not going to use BEDMAS backwards for exponentials, and what I mean by exponential is when you have f at x and you have b at x, where we have the base and you have the x, and this is an exponential function. So the three situation is when the variable is on the base. So as you can tell, I have x squared, x cubed, the base is x. So not in the exponent. To solve, you must isolate by using, we're going to isolate by using BEDMAS backwards, or sometimes you might see SEMDEB, and all that means is I'm trying to say BEDMAS backwards. So that's our first method. Second method, when the variable is in the exponent, not on the base, to solve you must, well, what we're going to try to do is to try to match the bases. Okay, we're going to match the bases to adjust to equate the powers, and you'll see that as an example. So lastly, you have when the variable is in the exponent and bases cannot be matched, you must use trial and error. And so keep in mind that next year, this will be used with, you're going to be using the log button, and there's a unit dedicated to logarithm function. And you'll learn how to do it algebraically or using the calculator and not the trial and error way. Okay, so these are the ways we're going to learn in this grade. So for question 1, we notice that we have 2 to the exponent 2x equals 8. So for this example, I'm noticing that this is an example where it's not that the bases the variables are on the base, but it's my second example where I have the variables in the exponent. Because that is the case, I'm going to do the matching bases method, all right? And what I noticed is that with the 8, I could somehow rewrite the 8 so that it has a base of 2. How do I do that? Well, 2 to the exponent of what equals 8? Well, 8 can be rewritten as a power of 2. So I'm going to go ahead and do that, and I will get 2 to the 2x is equal to 2 to the 3. And so as a next step, what you're going to do is, and this is one of the most important steps, is that you're going to ignore the base if it appears once on each side. Meaning that if I have 2 as a base on the left, 2 as a base on the right, and it's one term equals one term, that means I can ignore the base and just look at the exponents and compare them. So my next line, I will get 2x equals 3 divided by 2 on both sides, so I can get the x by itself, and I'll get x equals 3 over 2, like so. And that's my final answer. And so you could do a check on your calculator, but basically what you would be doing is that 3 over 2 times 2 is 3, and 2 to the 3 is equal to 8. Question B. So for x to the exponent 4 over 5 equals 81, the first thing I'm going to do is write the b, the first part, in terms of a radical sign. So I'm going to move that so that the numerator is here, and the 5 is on the radicand part at the front, and it's going to equal to 81. I know I want to get my x by itself, so I'm going to put an exponent of 5 on both so that it'll cancel those out. I will now get x4 equals 81 to the exponent 5. And then next, I'm not going to evaluate what 81 to the 5 is because that's going to be a really big number. I'm going to 4 root it so that I can get the x by itself. And when I do that, I will get x is equal to, what is the 4th root of 81? And when you do that, you will get a 3. Because 3 times 3 times 3 times 3 is equal to 81. And I'll get 5 as the exponent. And therefore, x is equal to 243. Part C. we have 3 to the exponent x is equal to 12. So I am noticing that, unfortunately for the 12, although you might be tempted to say, oh, it's divisible by 3 and 4 and whatnot, I can't write it. I can't rewrite 12 as a power of 3, meaning my base, I can't rewrite it so that the base is a 3. And so in this case, I will need to use the third method, which is the trial and error method. So I'm going to try a bunch of numbers. So, I've gone through this before, so it's going to work out almost perfectly. But what is going on in my head is, well, let me try, let's say, some number like 3 to the 3. And that's going to equal 27. And I know that's too big. And I might go one digit underneath. And so I have a 9. But 9 is too small. And it's like the golden log effect, and you want to go get it just right. And so you might try 3 to the exponent 2.5, and it's about 15.588, and that's also too big. And you're going to kind of repeat this process, and you might get close to the value, and it'll be somewhere like 3 to the exponent 2.25, and so I get 11.844, which is pretty close to the 12. So that's a trial and error method, and you're trying to get as close to that value as possible. And as my therefore statement, I'll write therefore x is approximately equal to 2.25, or you might have picked a different value, like x is equal or approximately equal to 2.27. Right? So you're trying to show your work and kind of justify why you're getting these values and why you're stopping at that point. Okay? Question 2A. So every time I see these, so question 2A, every time I see these as the exponents, I tilt it so that the negative is on the numerator. That's the first thing I would do. Second, I don't want negative exponents, so I want to get rid of that as a first part. So if you recall from the previous lessons, I am going to move its place to the denominator and rewrite it so that it has an exponent of a half, and I have 9 over 16 on the right. Next, I'm going to rewrite it so it looks like a radican, and it's a square root of x, and I have that. So what do you think you might do next? Well, I don't really like keeping it as fractions, so I'm going to cross multiply. And next, I have 16 is equal to 9 square root of x. Next, what am I going to do? Well, I want to get x by itself, so I want to divide by 9 on both sides. And I'll get square root of x equals 16 over 9. So I'm getting really close. So last step is, well, anytime you want to get rid of a square root, you want to square it, because that's going to get me that x by itself, because these are going to cancel out, right? And so I am going to get x is equal to, well, 16 squared is 256, and 9 squared is 81, and that is my final answer. Okay, question B. So I have 3 cube root of x plus 5, and then 4. All right, I want to make sure I put brackets here. It's a binomial, right? I don't want to make any mistakes. Well, to get rid of cube root, I should cube it on both sides. And when I do that, I will get x plus 5, just because these will cancel out. And I'll get 4 cubed, which is equal to 64. And I just need to get my x by itself. And so x is going to equal to 61 in this case. Oh, not 61, but 59 in this case. All right, question C. So 37 is equal to 1 plus 6x to the exponent of 2/3. So I want to get my x by itself, right? But I'm doing BEDMAS backwards, and I want to get rid of that 1. So I have 36 is equal to 6x to the exponent of 2/3, but at this point I'm going to rewrite it. So I write my 6x, and then I'm going to keep my numerator, and then I'm going to replace it so that it's in the radicand sign. So that's my next step. Next, how do you get rid of that 3 root? Well, you can take the cube of both sides. That way, I will get 36 to the exponent 3. Those will cancel out. And then I will get 6x squared, just like so. At this point, again, I'm trying to get rid of, and I'm trying to get x by itself. So there's no point of, let's say, me cube rooting these two things, because it's not that I want 36 by itself. I want to get rid of the things on the x, so I'm going to square root it. And even though I don't have to, I'm going to put a 2 there just so you know that I'm clearing that side. And so then I'm going to get 6x on the left side. Well, square root of 36 is going to be a nice 6, because 36 is a perfect square. And so I have this, and I'm almost done. How do you get x by itself? You're going to divide by 6 on both sides, and x is going to equal to 6 squared, because I'm going to subtract the 3 and the 1 by quotient law. And finally, I have x is equal to 36. All right, so some kind of math. All right, so this is an optional math talk we could have, and about what is pi and what is e, and you can look at these resources if you're interested after this little blurb. And what I got from this is that basically pi is when you do circumference divided by diameter, and regardless of the size of the circle, you'll always get this value of 3.14. And the pi is one of the Greek alphabet letters. Meanwhile, what is E? Well, E stands for Euler's constant, and it's about 2.718. And the way the video explains it is, if I had $1 and I put it in the bank, and it was put in a way that it was compounding based on this formula, what you get is that if we assume that it's compounding, meaning it keeps being added by interest, and not for 1 year, not semi-annually representing the 2, not quarter annually, or not monthly, not daily, but let's say you go to infinite number of amounts. When you start off with that value 1, and if you do it to an infinite amount according to this formula, you will get about 2.718. So that is kind of a comparison of where that Euler's constant is coming from. On to our lesson. And so pi is called pi. I mean, that's how you write it, and then this is how we say it. And pi is 3.141592654. Is used with anything circular, right? And I gave you that circular background, all right? So for E is called Euler's constant. And E is equal to 2.71828182. And I would invite that, just like you know where the pi is on the calculator already, try to see where the E button is on your calculator so that you are able to get 2.718 without having to memorize it. Okay, so question 3A. Practice trial and error method to solve for the x. So as you can imagine, I see the x and I want to isolate it. Well, in order to isolate it, I need to do BEDMAS backwards. So what am I going to do? I'm going to subtract the 5. And so I'm going to get 6x is equal to 5. So hopefully you're with me so far. And because they told me I'm doing my trial and error method, that means, again, I'm trying some values that might be reasonable. So I'll try 6.1. And you should be showing your work just so I can see your thinking process and your work behind how you're getting this number. So now, because that number is too big, I'm going to try 0, and I get 1, and that's too small. And you're going to work through it. I mean, there's no right or wrong answer per se, but I mean, we should all be getting closer to the estimate that I present to you. Okay, so next I'm going to try a slightly higher number. So I have 0.9 and I have 5.015. So I'm getting closer, and therefore I'm going to write x is approximately 0.9. Right, so that's the trial and error method. And I mean, is it my favorite method? Probably not, and I prefer doing the log way. But we'll learn that in grade 12, advanced functions. So next, for part B, I am going to replace that e for now by plugging the e value in to help us, because otherwise it looks like a lot of variables. And so I have 2 bracket 2.718, and I'll put that value to the exponent of x equals 17. Well, we know that we want to get that x by itself, and the base of e, or 2.718, is part of it. So I need to isolate that. How am I going to do that? Well, right now that whole thing is being multiplied by 2, so I'm going to divide by 2 on both sides, and therefore I will get 2.718x is equal to 8.5. And at this point, I'm going to try again some trial and errors. So 2.718, I might plug in a 2, and I'm realizing I am getting values that are too small. So I need to try a different value after that. So maybe 2.718, 2.2, and I have 9.0222. So that's too big. So it's the golden log effect, and I want to get closer. And as you try more values, you'll notice that maybe 2.1 might be our best guess. Okay. Question C. So we have this fancy equation going on with everything going on. And so sometimes when we see things that are complicated, and we've seen these kind of examples in previous units, I'm going to let's say x equal 2m minus 1. That way I could just treat it as a little x. That way I will have 3, and then the 2 as the base, x plus 2 equals 14. All right, and what I want to do is I want to isolate this part, and so that I can eventually get the x by itself. So again, by BEDMAS backwards, which means I need to do addition or subtraction, I need to subtract by 2 on both sides, and I get 2 to the exponent x is equal to 12. So as you can tell by BEDMAS backwards, I need to divide by 3. And I get 2 to the exponent x is equal to 4. So note right away, you should realize that x is equal to 2 because 2 to the exponent 2 is equal to 4. But keep in mind, I'm not done yet because I wasn't asked to solve for x. I was asked to solve for m. And so what I'm going to have to do is to use the let statement that I had originally made and solve for m. So I will get x is equal to 2m minus 1. So therefore, 2 is equal to 2m minus 1. I'm going to get m by itself by doing this. So I get 3 equals 2m. I want m by itself, so I want to divide by 2 on both sides, and m is equal to 3 over 2. Highlight that.